I'm Dan Freed, director of the Harvard Center of Mathematical Sciences and Applications. We're a center on campus. We engage in mathematics and interaction with lots of different sciences. We run different programs and special lectures such as this. I encourage you to check out the website and check out our YouTube channel where you'll find many interesting lectures, including previous ones in this series. So today this series is in honor of Raoul Bott, a very colleague that many of us remember very fondly. And we're very pleased to welcome Dennis Gaitsgory from Max Planck Bonn, who will talk about function-theoretic consequences of geometric Langlands.
Thank you very much. Oops, it's very loud. It's okay. I'm very honored to give this lecture series. I was debating whether or not I should add a personal anecdote about Bott. All right. I don't know how funny it is. So it was, the year was 1998, and Kazhdan and Ettinghoff were running the seminar Quantum Field Theory, and Bott was there. So, and Pavel was explaining something, and I piped up by saying that I complained it was not sufficiently functorial, and Bott looked at me, oh, this categorical guy. So you're gonna see some of it. Anyways, so there'll be two talks, and the first one I've given a bunch of times, so I apologize to those of you who've heard this before, and the second one is new. All right, without further ado, function field Langlands. So we work over ground field, which is FQ bar, but our objects are defined over FQ, and I'll encode that by using the Frobenius. So X is a smooth complete curve over this field. And G is a reductive group over this ground field. And so our object of study is what I call bun G. It's the moduli space of principal G bundles on the curve. So space, but technically it's not a scheme, it's an algebraic stack. All right, so as I said, we regard it as an object of algebraic geometry over FQ bar, but it's defined over FQ, so we can take its FQ points. And I'll now introduce the object of study in the theory of automorphic functions. So we consider the set of FQ points of this. It's an, I should say, set of isomorphism classes, so that it's an infinite set. And we're interested in just functions with finite support on the set. Well, with coefficients in arbitrary field of characteristic 0. So for tomorrow, we'll be primarily interested in C coefficients, but today we take QL bar coefficients. And so the goal of this part of the Langlands program is to describe the set as explicitly as we can in terms of what we call the spectral side. And the spectral side has to do with the Langlands dual group. So let me put it here. So G check is the Langlands dual group. It's defined combinatorially in terms of G, but we regard it as an algebraic group over the field of coefficients. And coefficients in this case is QL bar. And so I'll write the shape of the answer, and then I'll explain the ingredients as we go along in this talk. So you'll have to believe me for the next half hour that there exists something, there exists an object of algebraic geometry over QL bar that classifies unramified Galois representations into G-check. I prefer to call them local systems. So I'll write it logsys G-check arithmetic. It'll be an algebraic stack. Over the field of coefficients QL bar, whose points are homomorphisms from, well, I wanted to write pi 1, but it's not the Galois group, it's the Weil group. So like if you remember this part of algebraic geometry, if you have a variety over a finite field, its fundamental group maps to the Galois group of FQ, which is z hat, but we take the z inside z hat. So the points are homomorphisms from the Weil group of the curve to this G hat up to conjugacy. So it's an object of algebraic geometry, and here is a very naive guess, which happens to be slightly incorrect. But it's incorrect in a very naive, a very interesting way. So kind of very naively, what you will do, you will just take this object of algebraic geometry and take global functions on it. So it's like a very naive expression to the fact that kind of automorphic forms are parametrized by Galois representations, and just if you imagine this set was discrete, you would just take a vector space spanned by isomorphism classes of such. So this is Langlands conjecture, which is, as I said, not correct, and I'll say how to correct it in a minute. But even with the correction, it's still a conjecture. We can't quite prove this. We prove that instead of this whole thing, we have to take just some of its connected components. We don't yet know that we hit all of them. But here's the correction. So you have to take global sections, but not of the structure sheaf, but of the dualizing sheaf, so of omega. And so this will play a particularly prominent role in the talk tomorrow. So you can play with it, and so you can ask the following question. What about if we're interested not in all functions, these are called automorphic functions, but let's say in the cuspidal ones, whatever they are. I'll talk a lot about cuspidal functions tomorrow. So can we at least say that there the difference between O and omega goes away? So you can naively ask if this is the same as, well, sections on irreducible local systems. And these irreducible local systems, they sit discretely. It's really disjoint union of points modulo finite groups. You can ask if this is true, and this is still false. It's kind of the fact that you have omega here makes this not true. So, like this is true for a specific case when the group is GLN, but it's false for other groups. So this replacement of O by omega is actually kind of very substantial. All right. And so the goal of this talk is to kind of outline the main steps in the proof of this thing. By the way, you're very welcome to ask me questions. If you can generate the question, please ask one. All right, so yeah, I should say that all of this is a huge joint project. So the last bit is joined with Sam Raskin. And it's this particular isomorphism. So then it's all based on the geometric Langlands conjecture, which is joined with Arinkin, Beraldo, Campbell, Chen, Fairman, and then 1, 2, 3, 4, 5. Kevin Lin, Raskin, and Rosenblum. So this is the geometric Langlands conjecture part. So again, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and there is another input, which is AGKRRV. So it's Arinkin, Kazhdan, Raskin, Rosenblum, and Warshawski. So this is around 900 pages. This is around 350 pages. You can imagine that's a lot of writing just to prove this one equality. All right. Okay. So our strategy will be as follows. We'll establish a certain equivalence of categories, and then we'll apply to it the procedure of categorical trace and deduce this isomorphism of vector spaces. So that's what we're going to do. So let me now explain what categories we'll be talking about. So there is the geometric side and the spectral side. So on the geometric side, the category we're interested in has, well, we denote in the following way: sheaves on Bun-G with nilp. And so let me decipher what this means. So what does sheaves stand for? So we define sheaves on affine schemes. So these are take Q-aladic sheaves, Q-aladic constructible sheaves on an affine scheme S, and then you incomplete. So this is a small category, kind of, you can't take infinite direct sums, and here, and then we add all infinite direct sums and cones thereof. So incompleted. So I like to work in the world where one can take arbitrary direct sums. So now this is what you do for affine schemes. If you have not an affine scheme, not even a scheme, Bun-G, so what you do is the following. So sheaves on any y, so let me write the symbol and then explain. We'll write it as follows. It's the limit over all affine schemes mapping to a y of sheaves on this y. So what does the symbol represent? It means that to specify a sheaf on y is the same thing as to specify a compatible family of sheaves on all affine schemes that map to y, and the compatibility is with respect to pullbacks, and you have the freedom to choose shriek or star pullbacks. So if y is an algebraic stack, it really kind of, you get two theories which are equivalent to each other. So make your choice. So sheaves on S. All right. And so that's what it would be if I just took sheaves on Bungee. But then there is this subscript nilp, and so this has to do with the following. So if you have an arbitrary scheme of stack Y, and you have a sheaf on Y, you can attach to it its singular support. So it's a theory that has existed for a long time due to Kashiwara and Shapira for sheaves in the topological context, and was developed fairly recently by Bellinson and Saito in the Elade context. So singular support is a subset inside the cotangent bundle of Y. And vice versa, if you fix a subset in the cotangent bundle of Y, you can consider sheaves sub n of Y. It's a full subcategory that consists of objects whose singular support belongs to this given n. So now, we do exactly this procedure where nilp refers to a particular subset in the cotangent bundle of Bungee. But let me say what it is. So T star of Bungee, well, has another name. It's called the space of Higgs bundles. So let me tell you what they are when the group is GLN. So example, for G equal to GLN, so just Bungee classifies rank n vector bundles on our curve. So I'll write in curly brackets M. M stands for a vector bundle. And now this Higgs classifies pairs. A vector bundle plus an endomorphism, but valued in the canonical line bundle on our curve. So M and alpha, where alpha is a map from basic deformation theory tells us that T star Bungee is the moduli space of such data. And now I have to tell you what nilpotent means. So nilpotent is the condition that alpha to the power n equals 0. So alpha to the power n is a map from M to M tensor omega to the tensor power n. And you want that guy to vanish. All right. So
what did incompleted mean?
So it's a formal procedure. If you have a linear category, you can create from it one that contains all direct sums in a universal way. All right. So this is our object of study on the geometric side. And now I'll start talking, and it's a category. And so you can make sense of it over an arbitrary ground field, and everything is functorial. In particular, if you R over Fq bar and everything is defined over Fq, this category carries an action of the geometric Frobenius. Call it prob. All right. So and now I'll start defining the relevant category on the spectral side. Any questions, please?
So the n in the nilpotent condition is the same as the n in the GLN. You don't want arbitrary.
Yeah, so this is, well, it's equivalent to a matrix is nilpotent if and only if high power vanishes, but this high power is enough to take to be n.
It is in general defined using the moment to the
Kitchen base?
it
moment map to where? So let me tell you what in general is. So in general, what you have is you have a G bundle and a section of the bundle associated with a coadjoint representation. And the nilpotent condition means that that section hits the nilpotent locus, the nilpotent cone. Thank you for the questions. Any more questions? All right. So the spectral part is a little trickier. So as I said, we want a modular space that has to do with L-adic, well, with local systems. And so I'm now doing the geometric theory. So these are local systems on the curve over FQ bar. So kind of the player here is not the Weil group, but the geometric fundamental group, which is profinite, and you're trying to create a modular space that classifies families of homomorphisms from it to this Langlands dual group, which also has a topology. It's not entirely clear how to do this, and so it somehow would delay the development of the theory, as people were not sure how to give this definition. And then one could give a very naive definition, and miraculously it works. So I'll now give one. So what I'm going to do, I'm going to introduce this object I'll call log_sys gcheck restricted. And restricted, it's the notion, kind of the name we made up for it. It refers to restricted variation. So, and it's an object of algebraic geometry. So it's a stack over QL bar. And it's not an algebraic stack. It's, formally speaking, it's a formal algebraic stack. So it's a quotient of a formal affine scheme by a group. So I'll now say what it is. So, but before I do this, I want to motivate it a little bit and give you the definition of the stack of local systems in some more familiar contexts. So suppose for a second that X is a topological space. And we want to give the definition of the space of kind of topological local systems on it with respect to Langlands dual group, and I call it Betty. So in this case, so we're classifying homomorphisms from the fundamental group of our X, which is a discrete group, and it's kind of easy to make it into a modular problem. So and here is the definition, if you unwind kind of what. So it's an object of algebraic geometry over the field of coefficients. So and as Grothendieck taught us, to specify an object of algebraic geometry, all we have to do is to specify what its R points are for an arbitrary ring R. So again, just let me emphasize that. So we're in a topological context, and here you can take your coefficients to be an arbitrary, let's say, field of characteristic 0, E, and in this case, R is an algebra over that field of coefficients. So in our case, our field of coefficients will be QL bar. So in any case, so here's what it is. It's a groupoid of symmetric monoidal functors I should also say right exact, all the technical words, from the category representations of gcheck to the category of R modules within Betty sheaves on your X. So here, X was a topological space. You consider sheaves in the topological sense of E vector spaces, where E is your field of coefficients. and you consider sheaves with an action of R, or you can equivalently write it as sheaves of R modules. And this is a symmetric monoidal category using tensor product, and you are considering symmetric monoidal functors from Rebnicek to here. And so Tanakian duality tells you that this is exactly this R points of the space of local systems. So here's another context in which we know what local systems are. So let X be an arbitrary algebraic variety over a field of characteristic 0. So in this case, one defines the stack of de Rham local systems. So these are vector bundles with a connection. And so here is a definition. So it's the same kind of thing. You write symmetric monoidal functors from Rebnicek, but you change the target. It will be R modules in the category of D modules on X. And so this gives you the usual notion of de Rham local system. And so in our Eladic context, we just mimic this. And we define, so loxis restricted by saying that home from spec R, where R is a commutative algebra over QL bar, this is symmetric monoidal functors from Rebnicek to R modules inside sheaves on X. And sheaves on X means Eladic sheaves left completed. And here it's really important that we took the left completion, because if we didn't, there wouldn't be any R modules. So R is typically infinite dimensional, and you would not be able to have some kind of interesting action of an infinite dimension algebra on a constructible sheaf. Here it's really important to sorry, int completed. Sorry. So this is some gadget in algebraic geometry, and it looks kind of awful. So for example, it has infinitely many connected components, and each of these components is, as I mentioned before, is a quotient of a formal scheme by an algebraic group. So it's like kind of not a nice object of algebraic geometry, but so one can still work with it. All right. Please.
Yeah. So the Bungie and also this LS, they are like, are you thinking about them as value in like spaces or sets as opposed to categories? Like, are you forgetting the more like symmetric into the functors forms a category?
So excellent question. So you're tempting me with a more detailed answer than I was planning to. So there is geometric side and the spectral side. Bungie lives on the geometric side. And the geometric side, we're dealing with classical algebraic geometry over the ground field, so not derived algebraic geometry. So, and Bungie is valued in groupoids. So it's not sets, but groupoids. So on the other hand, on the spectral side, we'll be dealing we'll be dealing with quasi-coherent sheaves, and they are sensitive to the derived structure. So, all of the objects that we introduce are objects of derived algebraic geometry, and there, and when it takes, say, R must be an affine derived scheme, and when you take even maps between two affine derived schemes, this is typically infinity groupoid. So you have to input the entire higher algebra into this business. So that said, if you have an object of derived algebraic geometry, it makes sense to say that it's an Artin-1 stack. And it is. So it's not 2, it's 1. So far, very good questions. Can you give me one more, please?
Why in this definition you don't need white feedback?
I do.
Then why do you call it restrictive evaluation? What's that?
Again, it's a very tempting question. Okay. So let's look at these two definitions, but instead of so now imagine here X was not a topological space, but algebraic variety. And suppose instead of Betti sheaves, you took, again, int completion of constructible sheaves. You could do that. So it'll be a Betti version of this Loxis restricted. And you can ask how that is related to this Loxis Betti. So it's a subfunctor. And so here's what the subfunctor looks like. You take this nice Loxis Betti, and you looked at loci with a given semi-simplification, and you take, so for every given for every semi-simple local system, consider the subset of local systems with the given semi-simplification and take the formal completion of it and take the disjoint union. So that's what it looks like. Loxist restricted looks in the Betti context. Again, if I work instead of all Betti sheaves, but in completion of constructible sheaves. And similarly here, if instead of all D modules I took int completion of holonomic D modules, it'll be exactly the same picture. I took this nice moduli space and I'll break it apart into formal completions of loci with a given simplification. Restricted variation means that I cannot vary my monodromy arbitrarily. I kind of stay in the formal neighborhood of a given semi-simplification. So, and in the ladder context, I don't have the option for these nice moduli spaces. I only have this guy, which is inherently this huge disjoint union. Thank you for your question. Give me one more. Oh, great. Yes, so it's another great question. So let's take R to be the field, and you can ask, so R will be the field, you have a symmetric monoidal functor, and you can prove exactly according to what you said, using what you said, is that the image will, here it will land in locally constant sheaves. Here it will land in least D modules, and here it will land in local systems automatically. So I didn't have to specify, that's automatic, just because, if you wish, this category has duals. All right, let me proceed. All right, so I want maybe this blackboard. So now I'll state the geometric Langlands conjecture, and what it says is that this category is equivalent to, well, the geometric object is Loxis G-check restricted, and I should put here prime to indicate that for now we don't know that we get all connected components, but let me just forget it. So naively, I would write quasi-coherent sheaves. But this is not quite true. So what you have to do, you have to replace it, kind of renormalize this category, and write int coherent sheaves with nilpotent singular support. So this nilp has nothing to do with this nilp, although kind of it's the same symbol. So I will say more about what incoherent sheaves are, and specifically with nilpotent singular support tomorrow. Just for now, view it as a slight modification of the category quasi-coherent sheaves. In fact, both categories have a T structure, and the bounded below categories are the same, so the only difference occurs, if you wish, at the cohomological negative infinity. And so the T structure here is what we call is not separated. There are objects that are all of whose cohomologies are 0, and yet the object is non-zero. So, but you have to make this modification in order for this equivalence to hold. So this is what we called geometric Langlands conjecture. So and that was proved in the context of D modules in this 9-author series, and Sam Raskin and I bootstrapped from it the version for elastic sheaves over a field of characteristic P. All right, so that's the first part, and it's true over any ground field, but now we are over FQ, and things are defined over FQ bar, and both sides carry an action of geometric Frobenius, and they act compatibly. And our next step is to perform the operation of taking the categorical trace, which I'll now explain what it amounts to. So what's trace? So if you have a finite dimensional vector space over your field and an endomorphism F, trace is the following. So you have, let's write V tensor V star. It receives the unit map from the ground field. Then you apply your endomorphism along one factor, tensor identity along the second factor. You go to V tensor V star, and then you apply the evaluation map. You can go back to your ground field, and the composite is the trace. So that's trace in linear algebra. Now you note that this makes sense in an arbitrary symmetric monoidal category. So if O is a category and little o is an object which is dualizable, and dualizable means that there exists an object called O, little o dual, and maps from the unit to the tensor product of O with a dual called unit map, and evaluation map back to the unit that satisfies the usual axioms. And if you have F, which is an endomorphism of your O, to it you will be able to assign the trace of F, and I cannot withstand the temptation of asking the audience, the trace is what? In arbitrary symmetric monoidal category, the trace of an endomorphism of a dualizable object is who? Rather, what does it belong to? Yeah. Like here, it was a scalar, which is an endomorphism of the one-dimensional vector space. All right. So now, what symmetric monoidal category will we apply it to? So the O that we'll take is what we call DG-cat. It's linear categories over our field of coefficients, and DG means that, well, it's categories in which we can do homological algebra. Not a million categories, but really something more flexible. So first of all, it has a symmetric monoidal structure. You can tensor two DG categories together. So this notion that was developed by Jacob Lurie. Let me explain to you how it works. So here's a typical example of a DG category. If you have an associative algebra A, you can consider A modules. That's a typical object here. And if you have two algebras, you can take A1 mod and ask how to describe the tensor product of A1 mod with A2 mod. And the definition is rigged in such a way that it's just modules for the tensor product associative algebra. And so over there, so in order to calculate the trace, your object needed to be dualizable. And such objects are dualizable. Let me tell you what the dual is. So the dual of A mod is modules for the opposite algebra. And this unit and co-unit map looks as follows. So the unit object here is vect. So I have to specify a map, a functor from vect to A mod tensor A op mod, which we said is the same as A tensor A op mod. And the functor from vect to anything, so vect is a unit object, is the same as to specify an object in the target. And that object in the target is A as a bimodule over itself. So K gets sent to A. That's the unit, and the co-unit is is the functor of tensor product. So we write it A mod tensor A op mod. It's the functor to vector spaces that if you take a left module and a right module, it gets sent to the tensor product of the two over A. So why am I going into such great detail in describing the trace? Because I want to perform one calculation. So let Y be reasonable object in algebraic geometry. So something like algebraic stack. In our case, it would be this log sys. So not necessarily scheme. And I'll consider the category quasi-coherent sheaves on Y. And let us be given a self-map phi from Y to Y. And then we can consider the functor of direct image with respect to phi. So it will be an endofunctor So what I want to do is calculate the trace of this endofunctor wait a second. So we said the trace in the symmetric monoidal category, somebody said it's the endomorphism of the unit. So in this case, trace is what? So trace of an endofunctor of a category is what kind of thing? What does it belong to? No, it has nothing to do with Y. Remember, it's supposed to be an endomorphism of the unit of my symmetric monoidal category. Yeah, so it's the unit in DGCAT is vect. So it's an endomorphism of vect as an object of DGCAT, but home from vect to anything is the object in something, in that something. So it's a vector space. So it's a vector space, but the question is which one? And so here's the answer. It's global sections on the fixed points of Y of the structure sheaf, global functions. So I want to perform this calculation, and one learns a lot from this calculation. Well, So I have to run this procedure: unit, apply, and co-unit. But to do this, I have to know what the dual of quasi-co-y is. Well, we know what dual of A mod is, and quasi-co, well, what's quasi-co? It's basically glued from modules. So the claim is that quasi-co is actually self-dual, and here's how the unit and co-unit maps look like. First of all, by this Lurie's recipe, quasi-coherent sheaves on Y times quasi-coherent sheaves Y1 and Y2 is always quasi-coherent sheaves on Y1 times Y2. So, and here's how the unit looks for given Y. So it's the following procedure. So it's supposed to be a functor from vect to quasi-coherent sheaves in Y. And here's what this functor is. So remember, this is the same as quasi-co-y times quasi-co-y. So here is the functor that sends the generator to the structure sheaf, i.e. it's pull back from the projection from Y to the point, and here it's direct image with respect to the diagonal map. That's the unit. And the co-unit looks surprisingly similar. It's a map from this tensor product, which I can think of as quasi-coherent sheaves on Y times Y, back to vect. And what you do, you pull back with respect to the diagonal map, and then you take global sections, which is the same thing as push forward to the point. And with this, let's try to calculate the trace. So what are we supposed to do? So instead of writing quasi-co, I'll be writing spaces on which I'm taking quasi-co, and I'll be using vertical maps for pullbacks and horizontal maps for push forwards. So I start with point, I pull back to Y, then I take direct image with respect to the diagonal, so that's my unit. Then I apply my phi, go to Y times Y, and then I apply pull back with respect to the diagonal, and then I apply push forward to the point. So when I take quasi-co, pull back, pull back, push forward, and it'll be a map from sheaves on point, which is vect, sheaves on point, which is vect, which is a vector space. But now, so here we have two push forwards. It's the same. So you can, this composite map is the graph of phi, and there is base change. So we do push forward and then pull back. And that's the same thing as first pull back to the fiber product and then push forward. And the fiber product is exactly the fixed points of phi on Y. So pull, push is the same thing as pull all the way and push all the way. And so what we do here, you pull back, you create the structure sheaf, and then you take its global sections. And that's how we get this answer. So that's one calculation I wanted to show you. All right.
Question?
Please.
So this fixed point is kind of derived, right? So in particular, the lattice identity, this is like the Harshal.
It's exactly the Harshal homology. All right. So what I want to do, I want to take traces of the Frobenius on the left-hand side, the right-hand side. The category is equivalent, the endomorphisms are compatible. If I take the traces, I get isomorphic vector spaces, and I want to get some mileage from it. But first, let's try to take the trace of the Frobenius, or maybe let's try to take the trace of phi lower star on sheaves on Y. It's almost the same thing as here. The difference, instead of quasi-coherent sheaves, I'm taking elliptic sheaves. And you can try to run the same argument, but one thing will fail, And what will fail is this. So while it's true that quasi-coherent sheaves on y1 times quasi-coherent sheaves on y2 is the same as quasi-coherent sheaves on y1 times y2, it's completely false for L-adic sheaves. And what you'll do, you'll only get a map in one direction. So you can run a similar procedure, and what you'll see that this will always map to cochains on the fixed point set of y with values in the dualizing sheaf. So it's a sheaf cohomology of the dualizing sheaf on the fixed point set. But this map will typically not be an isomorphism. So in particular, you can take y to be defined over fq, and you can take this to the Frobenius, and you'll see the trace of Frobenius on sheaves on any y. So here y is, for now, quasi-compact. So if you take Frobenius fixed points on a stack, it'll be discrete as an object of algebraic geometry. It'll be just fq points of the stack. And so what you're going to see, it'll be this vector space will be functions on the set of fq points of y with L-adic coefficients. So this omega goes away because the object is algebra geometrically discrete. So you'll have a map, but it's not at all an isomorphism. And when y is not quasi-compact like Bungee, you'll have functions with finite support. So let me put here Bungee. But, so if you were to take the trace of Frobenius just on sheaves, you'll have a map, not an isomorphism. But we don't have just sheaves, we have sheaves nilp. So that receives a map from what we're actually interested in. So we can consider the composite map, and here comes a pretty surprising theorem, and so which says that this composite map is actually an isomorphism. So this is the theorem from this paper that I mentioned, AGK-RRV. It's kind of isomorphism that at the time nobody expected. So when I told this to Drinfeld as a conjecture, he said, like, forget it. Like you have to prove everything else in the world before you'll be able to prove this. But then miraculously it worked out. So it's kind of very strange thing that you can restrict your sheaves, take the trace of the Frobenius, and get exactly functions on the underlying set. All right, so we worked out the trace of the Frobenius left-hand side, and we got exactly the vector space that we're interested in. It's a space of automorphic functions. So let's talk about the right-hand side. So let me introduce the notation. So we had our loxis restricted, and it's acted on by the Frobenius, and I denote the Frobenius fixed point set by loxis arithmetic. So this is loxis arithmetic that I mentioned at the beginning of this talk. And while this is a formal algebraic stack with infinitely many connected components, this was an honest algebraic stack, quasi-compact. So somehow this taking fixed points of the Frobenius eats up all these formal directions. So if it were quasi-co, I would know the answer. It's already written here. So trace of Frobenius on quasi-co, loxis restricted, is global sections of the structure sheaf on loxis arithmetic. But the equivalence is not with quasi-co, but with this int-co. And there's a parallel computation to what I did here, which says that if you do this trace of Frobenius on the int-co category, and also when it restricts the singular support to this nilpotent cone, what you're going to see is global sections of the dualizing sheaf. And so we are more or less done. So, oops, well, I shouldn't have erased that. So we have this equivalence of categories. We take the trace of the Frobeniuses on both sides. And these become isomorphic vector spaces. And as we said, this is by A.G. K.R.V., which I wrote and erased. This is compactly supported automorphic functions. And this is global sections on this Loxis arithmetic of the dualizing sheaf. And hence we obtain the isomorphisms of vector spaces that I announced in the beginning. So, and this is the answer, if you wish, to the unramified Langlands question from the 60s. So the space of automorphic functions in terms of Galois representation is what? And I'm saying what it is. Take this moduli space, take the dualizing sheaf, take global sections. End of first talk.